Every advanced chip you have ever used was cut and thinned by machines from two Japanese companies almost nobody outside the industry can name. Not designed, not lithographed, cut, ground, polished, diced into the individual chips that ship inside your phone, your car, your data center GPU. Two companies, Disco and Tokyo Seimitsu, together hold roughly 80% of the world market for dicing and grinding equipment. And here is the part that should make every AI investor stop and pay attention. Without their machines, an HBM stack cannot be built. A CoWoS package cannot be assembled. An H100 cannot ship. NVIDIA gets the headlines, TSMC gets the credit for packaging, but the wafer that becomes those packages first has to be ground down to 50 micrometers and then sliced apart by tools made in Japan. This is the dicing and grinding duopoly, the most invisible choke point in the entire AI supply chain. Today we will explain who they are, what their machines actually do, why their lead is structural rather than temporary, and why their order books have become a more reliable AI demand signal than almost any chipmaker forecast. Let us frame the problem. A finished wafer leaving a fab is a disk about 300 millimeters across, with hundreds or thousands of chips printed on it in a grid. Before any of those chips can become a product, two physical operations have to happen in this order. First, grinding. The back of the wafer is thinned from its incoming thickness of around 775 micrometers, down to anywhere between 200 micrometers for a normal chip, and as thin as 50 or even 30 micrometers for memory, dies that need to be stacked. Second, dicing. The wafer is cut into individual chips, each one separated cleanly without chipping the edges, without cracking the silicon, without contaminating the active surface. Both of these sound mechanical. Both sound like solved problems. They are not. As nodes shrink, as wafers get thinner, as packaging gets more aggressive with stacked memory and embedded silicon bridges, the tolerance window collapses. A grinding wheel that worked fine at 200 micrometers will shatter the wafer at 50. A dicing blade that produced clean cuts on bulk silicon will create micro cracks on a wafer that has through silicon vias. The machines that handle these problems at scale, at modern yields, are designed and serviced by Disco Corporation, founded 1937, and Tokyo Seimitsu, founded 1949, both headquartered in Tokyo. Together they ship the vast majority of dicing saws, grinders, and the increasingly important hybrid tools used by every advanced packaging line on the planet. Deep Dive 1. Blade dicing, the workhorse. The simplest way to cut a wafer is also the oldest. A thin spinning blade made of resin-bonded diamond particles, between 30 and 200 micrometers thick, runs along the streets between chips at tens of thousands of revolutions per minute. Water flushes the cut. The wafer is held flat on a vacuum chuck. It sounds straightforward. It is not. The blade flexes, it wears, it loads up with debris and starts to chip the edges of the silicon. Every fraction of a micrometer of chipping on the die edge is a future yield loss when the chip flexes in its package. Disco controls the entire value chain of this technology because Disco does not just make the dicer. Disco makes the blade. Disco makes the wheel. Disco makes the wear monitoring system, the cooling system, the spindle, and the software that learns from every cut and adjusts feed rate in real time. Tokyo Seimitsu makes a comparable product line under the Accretech brand, with a slightly different philosophy, more open architecture, easier to integrate into mixed lines. Between them, blade dicing remains the most common method used in packaging plants from Taiwan to Malaysia to the United States. And the consumable revenue from the diamond blades they sell as replacement parts is, episode after episode, more profitable than the dicers themselves. Deep Dive 2. Back grinding and Disco's signature TAIKO process. To stack memory dies on top of each other inside an HBM package, you need the dies to be physically thin. Modern HBM3E uses dies thin to around 30 to 50 micrometers, about the diameter of a human hair. The first generation of high bandwidth memory used dies around 80 micrometers. The trend is one direction only, thinner. The problem is that a 300 millimeter wafer, ground down to 50 micrometers, is structurally a sheet of glass. It warps. It cracks. It is almost impossible to handle. Disco's answer is a process they trademarked called TAIKO. Instead of grinding the entire back surface uniformly, the TAIKO grinder leaves a thicker rim around 3 millimeters wide around the outer edge of the wafer. The center of the wafer is ground thin, but the rim acts as a structural support, a frame holding a drumhead, which is exactly what the name TAIKO refers to. The result is a wafer that can be transported, inspected, and processed at 50 micrometers without breaking. There is no comparable product from any other vendor at the same maturity. Every major HBM producer, SK Hynix, Samsung Micron, uses TAIKO. Without it, the modern HBM stack does not exist in its current form. Tokyo Seimitsu competes in conventional grinding with strong share, but in extreme thin grinding for memory stacks, Disco's TAIKO line is effectively standard. Deep Dive 3, Stealth Dicing and Plasma Dicing, the post-blade era. As chips get smaller and the silicon they sit on gets thinner, the blade itself becomes a liability. A 200 micrometer street is fine for a blade. A 30 micrometer street is not. So the industry has moved to two newer approaches. The first is stealth dicing, a technique pioneered by Hamamatsu and now widely used by Disco, where a focused infrared laser is fired inside the silicon, creating a damaged plane under the surface that propagates as a clean crack when the wafer is pulled apart on a stretch tape. No water, no debris, no edge chipping. The second is plasma dicing. The wafer surface is coated with a protective resist, then etched with a fluorine plasma along the streets, creating a chemically clean separation that produces almost zero edge damage. Plasma dicing is essential for thin compound semiconductor wafers used in radio frequency chips and in some advanced packaging tiles. Disco and Tokyo Seimitsu both offer machines in both categories, and the customers buying them are exactly the names you would expect: TSMC, Samsung, Global Foundries, PowerTech, ASE, Amkor, and the in-house packaging lines at SK Hynix and Micron. The point is not that any single dicing method dominates. The point is that across blade, stealth, and plasma, every method is supplied by these two vendors. There is no third large supplier with mature, qualified equipment in production fabs at scale. Deep Dive 4. Why advanced packaging makes the duopoly stronger, not weaker. In the simple world of monolithic chips, dicing and grinding were unglamorous back-end steps. The chip got cut, the chip got packaged. Done. Advanced packaging changes the math. In a CoWoS package, the GPU and the HBM stack sit on a silicon interposer or a redistribution layer that is itself a precisely thinned and diced piece of silicon. In a chiplet package, multiple dies are co-assembled, each one requiring known good die inspection, each one demanding cleaner edges and tighter thickness control than monolithic dies ever did. In hybrid bonding, the technique that lets two dies be joined copper to copper at room temperature, surface flatness is measured in nanometers, and a poorly ground wafer is unusable. Every one of these steps pushes more value, more revenue, and more strategic importance into the grinding and dicing tools. Disco's revenue grew roughly 90% between 2019 and 2024, driven not by the number of chips made, but by how many grinding and dicing steps each advanced chip now requires. A monolithic CPU might pass through grinding and dicing once. A CoWoS packaged AI accelerator passes through grinding and dicing stages 5 or 6 times. For the GPU die, for the HBM stacks, for the interposer, for the package thinning, for the final singulation. The advanced packaging boom is a direct revenue multiplier for the duopoly, and it cannot be substituted around without redesigning the package itself. So who wins? The verdict, in the actual semiconductor industry view, has 2 layers. The first layer is Disco Corporation, ticker 6146 on the Tokyo Exchange. Disco controls the upper half of this market. Extreme thin grinding via TAIKO, the dominant blade dicing platform, the leading stealth dicing line, and a fully vertically integrated consumables business that sells diamond wheels, blades, and grinding stones that go into every machine. Disco's operating margins routinely exceed 40%, a level normally seen only in software or in monopolies. That is not a coincidence. Disco is a monopoly in everything but name across thin die grinding and high-end dicing, and the consumables stream means the installed base keeps paying long after the machine ships. The second layer is Tokyo Seimitsu, listed under Accretech, ticker 77209. Tokyo Seimitsu is the broader portfolio competitor, strong in conventional grinding, strong in dicing, and the dominant supplier of wafer probers for testing. Its share in pure dicing and grinding is smaller than Disco's, but it is the only credible second source the industry has. If you are a packaging plant in Taiwan or Korea and your line goes down, your two phone calls are Disco and Tokyo Seimitsu, in that order, and there is no third call. As a structural pair, they are the dicing and grinding choke point of every AI accelerator, every HBM stack, every CoWoS package shipping today. Their order books move with the same signal that drives NVIDIA and TSMC, and they are upstream of both. That closes episode 5 of the Forgotten Monopolies series. Across the last 5 episodes, EDA, wafers, substrates, KLA's inspection mode, and now dicing and grinding, a single pattern has emerged. The most fragile, most strategically important parts of the AI supply chain are not the chips themselves. They are the upstream tools and materials. 2 software companies decide who can design a chip. 2 Japanese companies make the wafer it starts on. 2 more Japanese companies decide whether it can be packaged. 1 American company guards the yield through inspection, and 2 more Japanese companies, the ones we just covered, decide whether the finished wafer can be cut and thinned. The next episode in this series will tie all of these threads together into a single cross-layer verdict. Which of these forgotten monopolies has the most pricing power? Which one is most exposed to a single customer? And which one would do the most damage to the AI industry if it disappeared tomorrow? If this episode shifted how you think about who really benefits from the AI build-out, subscribe, leave a comment with the company you think we should cover next, and join us for the series recap. Thank you for watching.